Good afternoon, everybody. I will give this talk on behalf of Kan Wang, who is downside in Australia and couldn't make it here. The other causes are Michael Meindl and Erik Schönemann and Werner Endele from ESA. I will talk about the improvements you can expect from high accuracy clocks when you estimate troposphere zenith parameters. I will start with an introduction of how we model the clock, how it helps for kinematic height estimations, that is well known. I will give a motivation why we went into troposphere here, then show results with and without clock modeling, quite evident, and do comparisons with what we think are some ground truth measurements, meteor data, which is not as nice as water vapor radiometer data we have for two of the stations. So, when I talk about high accuracy clocks, I talk about hydrogen masers uniquely. We need really the best possible clocks to call them high precision clocks in this context here. And we selected just a few of these stations that are connected to such a hydrogen masers. 6 of them, you see them on the right-hand side. And there are 2 ways to characterize this clock. For instance, the standard deviation of the clock estimates after removing a linear polynomial. That's one thing, you see it over here. And the area for these clocks is about 30 to 120 picoseconds, which corresponds to 1 to 4 centimeters. That means over one day, this is the type of noise you have. Another possibility is to look at the epoch-to-epoch changes, sigma E, and this is much smaller, obviously. You see it here. It's on the level of 10 to 20 picoseconds. This is almost at the phase noise level of 3 to 6 millimeters. So this gives us an idea how we can constrain the clocks, because these are some data we can get directly from the clock estimates. So our model is very simple. We take an offset and a drift, and we add a stochastic parameter P, which is there for every epoch, and then we do what we call relative constraints between the two subsequent epochs, and setting the difference to 0 as a pseudo-observation with a weight given there. And the most important parameter there is sigma R, which is, so to say, this sigma of the clock. We also put a very weak absolute constraints because we need this to make the system non-singular. Yeah, when we now look first at kinematic heights, so this is all about kinematic heights and troposphere, then we can see some of the results here with and without a clock model. You see them here with a clock without the clock model, and about 4 centimeters accuracy or precision if we have the clock models. This is well known. We have an improvement factor of about 2 to 3 in the kinematic heights due to breaking the correlations with the clock. Now, to go a step further, we were looking at the modified Allen deviation of these coordinates. So kinematic coordinates, look at them like clocks, and then see how they change when we change the constraint. And we start at a high level with no constraint, so this is a worst solution, and then you see that we go down to 1 millimeter constraint relative on the clocks, and you see that the improvement is quite dramatic. This is, let's say, well known, but what we were a little bit considering in special was this question here. Why this is so high at this level of about 0.5 to 2 hours, especially thinking of the fact that we had a zenith path delay sampling of 2 hours. So this seems to coincide, and so we thought we have to look into this in more details. It's clear that this has high correlations there, just to remind you of the station clock with a constant derivative, then the troposphere that is increasing with zenith angle, and the station height that is decreasing with the zenith angle. And all this depends very much on your constellation and the elevation cutoff you take. So you have to take as many data as possible in a large geometry. You have here 1 over cosine z, 1 over and here cosine z. So these 3 parameters are highly correlated, and it's clear the higher the time resolution, the worse you get. So Looking at this example from PTB, we thought that we will now increase the troposphere zenith sampling, which is a logical thing to do. And you see on the left-hand side that with no clock model, what we see when you go to 1 hour, 45 minutes, 30 minutes, 15 minutes, what you would expect. Things get worse and worse because we have less geometry, we have a shorter time to estimate the parameters, troposphere parameters, and so you see that in the high frequency end, you have a large scatter coming from these correlations. When we now look at the same example, but we take the clock with the constraints, then you see that first of all the bulge is going down, which is probably what we expected a little bit, but then what is more important, it just stays constant all over. That means we can resolve the troposphere to whatever degree of resolution in time without any impact on the kinematic station heights, which I think is a nice thing coming out of this clock modeling. When we now look into this, this is another example, Seber, just to show you the same picture, no clock modeling and clock modeling. So there is a huge difference there in how the things behave in the high frequency part. We can also look at the 2-in-1 plot. One example from August, one from November, and dashed lines are actually those you get when you do the clock modeling. So this is, in some cases, as for instance here, almost a factor of 10. Thinking that this system is highly unstable. Same thing with Seber, also 2 days, it shows exactly the same behavior. So we thought then we have to try to use these 6 stations to get something comparable. Because there is not much water vapor data available, we took meteor data, which is not optimum, but still, even with meteor data, you see from these 6 sites how things get worse in the comparison of the zenith delays computed from GPS compared to the meteorological derived values, that things get worse if you increase the sampling rate of the troposphere, which is obvious. But if you model the clock in red, you stay at more or less the same level, and you always have an improvement in these troposphere estimates. In view of the fact that meteor is maybe not the most appropriate thing to use, we looked at water vapor radiometer data here for Seber, and you see here the estimates we get when we do no clock modeling. I can now add the clock modeling, and as you see, these correlations are interrupted, so to say, and you get a much smoother behavior. And when you look at the water vapor data, then I will say on the left-hand side, you do not see really a very nice comparison, but on the right-hand side, it looks quite nice, with the exception of some sort of calibration offset we have here for this November data. When we look at meteor data, you see that the question is whether this can be used for any of the validations. In this case, it doesn't really fit nicely. But still, when looking at this water vapor radiometer series, we see the same behavior. When we go to high tropospheric resolutions, we get an improvement of the RMS, or RMS reduction, when we model the clock of 5 to 7 millimeters. When we are at 2 hours, there's still an improvement in the reduction of about 2 millimeters. So we see that there's a significant improvement in the zenith path delays coming from this clock modeling. A final test we did was on Onsala for 5 days. Again, you see here is a no clock modeling time series, then the one with clock modeling in red. And you see that especially these spikes are very heavily reduced. And we can also plot water vapor radiometer data, which shows a quite nice agreement with the clock model series. To put this into more quantitative way, you see here a table containing on the top without clock model, and on the bottom you have with the clock model, increasing the time resolution of the troposphere parameters from left to right. And you should always compare now, I hope you can do this, the red line and the green line. And you see that for all these values, we have an improvement in the comparison of the water vapor data with the GPS estimates. And the improvement in general gets better if we go to higher resolutions. This is a quite dramatic case, but more or less all these cases, every line is improved compared to no clock modeling. You see it also here from 50% from 1.5 centimeters down to 1 centimeter. So this leads me to the conclusions. Clock modeling not only improves kinematic heights, but also zenith path delays, which is, I think, obvious looking at the symmetry of kinematic heights, troposphere, and clocks in the middle. With clock modeling, there is no degradation of the zenith path delays whatsoever if you go to very high time resolutions. So you saw 15 minutes. I think you can easily go higher. And the comparison with Meteo, or more importantly, with water vapor radiometer data, shows that the zenith wet delays are improved in all the solutions when we use such a clock modeling. I think the next step will be to verify this with a much larger data set. Thank you for your attention.